So, so today we're doing chemical fundamentals. We're actually out of the statistics and quality control, and now we're getting into the chemistry behind analytical chemistry. So we're going to be using Le Chatelier's principle and partitioning and equilibrium to drive our analyte out of the matrix. So we want to separate our analyte from all the other things that interfere with analyzing that substance. So we're going to relearn pH and ice tables and all of those things today. Where does this fall in? Well, in the C's drug subcommittee, they developed these process maps. And so here's one from this scientific advisory committee on C's drugs. And so this is what the process map looks like. Now, I know you can't see that because it's such tiny type, but let me just explain some of the things that you see here. It talks about analysis. And so they have in here these little active boxes, and so you can see that we classify these materials like plant material, crystalline powder. Is it chunky? Is it a fungal substance? Is it a pharmaceutical or an illicit preparation? Is it a liquid? Is it a THC related product? Is it a gummy, tar, or waxy substance? And then there's other things like paper. LSD is sometimes deposited on the back of things like stamps, so it's not suspicious to have a stamp in your wallet. But if it has LSD on the back, can you lick that stamp? We used to lick stamps. Now everything sticks, right? So this kind of goes back to the day when they would put LSD on the back of a stamp, and you would lick that stamp, and there would be a way to get the drug. And then you could just sell stamps to people. And they possess this stamp. Well, that's not suspicious, right? But if they seize it, then they've got a stamp, and they test the back to see if there's LSD been deposited on the stamp. So that's an old school thing, or dipped cigarettes, other kinds of things. Then they go into the lab, and you have sample description, select it for analysis. There's preliminary testing, and then instrumental analysis, confirmatory testing. There's a lot of vocabulary, and you can see this again in this OSAC committee. But I wanted to point out some of the things we've already talked about. There's sampling plans, there's presumptive tests here, there's different kinds of weighing techniques, but then down here at the bottom, sample prep. And so that's what this whole lecture is about, this sample prep. So we're extracting the analyte, maybe it's a C's drug, maybe it's something else, from the rest of the substance, right? We get all these crazy, like a stamp. You can't just grind up the whole stamp and stick it on a GC. That doesn't make any sense. You want to extract the suspect analyte from the glue on the back of the stamp and then analyze your analyte. We leave the paper alone. We don't care about the paper, okay? Maybe we analyze the paper to see if there's some special thing about this stamp, but for the most part, we're after the analyte that tells us about the substance that they're selling. So the best case would be dilute and shoot, which is almost never the case. When you get a liquid sample, and maybe, I say almost never the case, maybe somebody's dissolved methamphetamine in a gas can. And so you've got a gasoline can that looks like gasoline, smells like gasoline, but they've dissolved a bunch of meth in there. So yes, you could dilute that and shoot that. It's an organic solvent. So that would be a rare case where you could just look at that analyte and run it through a chromatographic thing. But even then, gasoline's not that great. It's dirty, probably. Filter and wipe. Now you have a heterogeneous system. So you might wipe the table. Say we suspected drugs was prepared on this table. You wipe it with a filter paper, and then you extract it from the wipe. So that's heterogeneous. You have the substance on the paper, and you've got to get it off. Or the stamp example, heterogeneous. You got to get the analyte off the paper. Homogenization. How many people in their biochem labs or whatever do homogenization? Anybody? Like if you have a blood sample, you've got cells in there, you've got enzymes, plasma, all the stuff that's in the plasma, and some of these bodies are huge, and we want to disrupt the cell membranes and all of those things. So we have ultrasonic and also little homogenizers that kind of look like frothers. Have you ever seen a milk frother, a little spinny deal? You can put that in there. It's got little blades at the bottom, and it destroys the cellular membranes and homogenizes the sample so that your analyte isn't stuck inside a cell and doesn't get extracted. So you can homogenize it, you can centrifuge it down, and then take the supernatant, and hopefully your analyte is in the supernatant, and you can analyze it that way. And then we have the lab sampling. We covered that in great detail in the quality section. So we take these large samples and we make small lab samples that are representative. But for partitioning, this is what we're going to use. Chatelier is going to be our taxi driver, and it's going to drive our analyte from the matrix into a solution that we can easily test. It can also separate analytes from other interferences and from other analytes. So we might have a mixture of drug substances. If one is an acid and one is a base, we can change the pH of a liquid-liquid extraction and drive one of them into the aqueous phase and the other into the organic phase. And we can control which one goes where by changing the pH of the aqueous solution. So that's what we're interested in doing. That's the reason we're getting back into pH equilibrium, is because if we can understand pH, we have a basic substance, we put it in an acidic solution, it's going to go right into the aqueous phase, because you're going to protonate the base and it's going to be charged. And so if it's charged, it's going to go into the aqueous phase. If it's unprotonated, if it's not charged, it's going to go into the organic phase, because all these drugs are organic molecules. They interact with our enzymes and all the organic stuff in our body. And so they're organic molecules, but the way to get an organic molecule into the aqueous phase, which typically organics, oil and water don't mix, is to make them charged. Coulombic attraction, the charges, pluses and minuses, that is a stronger force than the oil and water type forces. Oil and water, the reason oil and water don't mix is the water hydrogen bonds with itself. And if oil was trying to separate water, that hydrogen bond is going to break, that takes energy, and then a few milli or picoseconds later, water reforms that hydrogen bond and pushes the oil out of the way. So it's really water excluding the oil. But if you have a charged part, like if part of that oil has got a little nitrogen on it and you protonate that nitrogen, now you've got a charged oil molecule. And it gets into water and it breaks the hydrogen bonds with water, but then they snap onto that charge and they help dissolve that oil. And so organic molecules, oil and water can mix if you can protonate the oil, if the oil has an amine on it. So that's what we're going to use. So we're going to learn again about pH and how to use it to partition our samples. So let's relearn our generic equilibrium constant. If we have this reaction, A plus B gives C plus D, and we have the number of moles out front, the little letters, then we have the equilibrium constant. And the number of moles becomes the exponent. And so we have products over reactants. And so if this is much greater than 1, again, the products are more than reactants, then the products are dominating. If this is much less than 1, then the reactants, the denominator is big, which means the reactants are dominating. If it's exactly 1, then it's 50-50. The reaction's right in the middle. It's half products, half reactants. And so if K is 1, then you've got sort of a strange situation. And so what? Why do we care? Well, this acid base and solubility, and we're not going to get into it, but also redox, equilibria are useful for partitioning analytes. And so we're going to just really stick with pH being the driver for our solubilities. So let's look a little bit about pH. Here's the pH scale, and here's Coca-Cola. And a lot of people make a big, this Coke Zero, make a big deal about Coke Zero. Now this is a fake label somebody put on the internet, because if you zoom in, it has caramel color, phosphoric acid, poison, aspartame. So somebody put poison in there because apparently they're against soda. But do you see that phosphoric acid? It is in Coke. It's just the pH of Coke, and Coke is slightly acidic using that phosphoric acid. And so maybe you've received I don't know, I don't know that we get the sort of internet chain letters or jokes and stuff by email anymore, because nobody takes the time to do that. They just make TikToks and stuff. But used to, we would get emails, from my Aunt Barbara. I would get all these emails from Aunt Barbara with jokes and stuff, or warnings. And I got this email about Coca-Cola, warning, don't drink Coca-Cola. And this was some of the claims in the email. In many states, the highway patrol carries 2 gallons of Coke in the trunk to remove blood from the highway after a car accident. It was not true, but anyway. You could put a T-bone steak in a bowl of Coke and it'll be gone in 2 days. Yeah, all this stuff. And they're like going crazy because of this acid that's in Coke. But look at the pH scale over here. Here's Coke, cola, and vinegar. There's a pH of 3. Okay. Look at your stomach. Your stomach is filled with hydrochloric acid. It has a pH of 1. It's 100 times more acidic than Coca-Cola. And you know what? If you put a T-bone steak in my belly, it'll be gone in less than 2 days. Because the stomach is incredibly acidic, so you don't have to worry about drinking Coke, maybe for other reasons, but not the phosphoric acid. Okay. Look at some of these other things. Wine is slightly acidic. Tomatoes are one of the more acidic vegetables. They have a pH of 4. Bananas. We have black coffee. Now, maybe a good Costa Rican coffee, which is more acidic. Is more acidic. It might be a little bit lower pH than 5. But rain, saliva, milk, human blood, and tears, those are all really close to 7. They're just slightly on the acidic side of neutral. And then you get into the basic compounds like baking soda, borax, milk of magnesia. What is that? Well, if you got a little acid reflux or whatever, you can take some milk of magnesia or Tums or something like that. And those are basic substances, and they help counteract some of the acid in your stomach. Look at household ammonia. It's close to 12. That's a very dangerous chemical. So if you have ammonia in your house, it's probably the most dangerous substance in your whole house. If you were to splash that in your eye, you could go blind. Like it would just destroy the proteins in your corneas and make them opaque and denature them. So ammonia is no joke. Household bleach also no joke. A lot of times it's sodium hypochlorite, and so it's the basic form of hypochlorous acid, and then sodium hydroxide is even worse. Now we can find sodium hydroxide in like liquid plumber and some of the drain cloggers, because the base, what it does with proteins is you have base mediated hydrolysis. So the base can attack the proteins and break them apart. Well, what is in your drain? What's clogging your drains? Your drains are clogged a lot of times by hair, and hair is protein. So you can put sodium hydroxide solution down there, and it breaks up the hair clogs and breaks up the grease and the oils and stuff and the soap residue, and then it breaks up that clog and lets the water flow. Now, it typically breaks up a tiny little hole. It doesn't break up the whole thing, because by the time it breaks up that hole, then the water drains out and there goes all your sodium hydroxide. But it's better to get it rooted out, like with the plumber. But this liquid plumber, you can pour into a drain clog, and it will decompose the greases, oils, and hair, and let it break through. So, little pH scale. Notice it goes from 0 to 14. Okay. And that's because we're in water. These are aqueous solutions. And so this is somewhat related to Kw, the autoionization constant of water. So we'll talk about that a little bit more later. A lot of these acids have multiple protons that can come off. And so if they have more than one acidic proton, and if the Ka values, the equilibrium constant for these acid protons coming off, are more than 2 or 3 orders of magnitude apart from each other, then the equilibrium just depends upon one proton at a time. And here's phosphoric acid. So if we're halfway to the end point of phosphoric acid with that first proton, we'll be at a 7.5 pH. So you can take the pKa, and that's the pH of that substance at 50% of that first proton coming off. What if we got past the first proton and we're halfway across getting rid of the second proton? The pH, or the pKa number 2 for phosphoric acid, would be 6.2 times 10 to the minus 8. So it'd be close to the pH of 8. And then the K3 would be close to pH 13. So trisodium phosphate, where we've pulled all 3 protons off of the phosphorus, then it's a very, very basic compound. It comes in at a pH of around 13. You can look at this exponent. So the first thing I misspoke. I didn't mean 7.5. It'd be a pH around 3 for the first proton. This would be a pH around 13. You can look at that exponent to see what the pH would be for that. So concrete uses a lot of trisodium phosphate. There's some cleaners you can buy at Home Depot for cleaning your deck or your concrete driveway. TSP, trisodium phosphate. You want to make sure you wear gloves, because again, that really basic substance can attack the proteins in your skin, and it will turn the fats in your skin into soap. And then soap is soluble in water. And so when you wash your hands, all of the moisturizing fats that are in your skin will be dissolved away. I did this stupidly. I was putting in a basketball goal and putting concrete in the hole, and I was just finishing up, smoothing out the concrete so it looked nice with my bare hands. I should have been using gloves. Okay, I thought it's just a small period of time. I'm not going to be working with it all day, so I went ahead and used my bare hands. And I could tell, it was really slippery. That slippery feeling is the oils in your skin being turned into soap. So it was my own fat in my skin being saponified, and that's why it felt slippery. I went and washed my hands thoroughly afterwards, but my hands, the skin dried out so much I couldn't straighten my hands for like a day until that oil was regenerated. And it looked like my hands were 100 years old. They were dry and wrinkly and demoisturized completely, and it was a very weird feeling. So that was dumb on my part, but that's how basic trisodium phosphate can be. So let's do some ice table review. Let's jump in here. So let's calculate the pH of a 2 molar solution of amphetamine, a super concentrated amount of amphetamine, but anyway. And then we're given the pKa. So let's review also this P function here. This P right here, P is defined as the minus log. Okay, so we take the minus log base 10. And so this pKa equal to 9.8 is equal to the minus log of the Ka. Is this ringing a bell? Yeah. And so how do we get rid of this log, right? We could change the sign over here, and we could say, I'm just going to do it here, and I'll erase it because I've got other things that are going to show up. So we could just move the sign over. So minus 9.8 is equal to the log of Ka. And then how do we get rid of the log? We put everything, we do 10 to the both sides. Anti-log is doing 10 to the both sides. So we do 10 to the minus 9.8 is 10 to the log Ka. So these things cancel. That's the anti-log. And so Ka is equal to 10 to the minus 9.8. So from now on, you should be able to do it like that. You get a pKa, a 9.8, you know that Ka is 10 to the minus 9.8. You do 9.8, change the sign, and hit anti-log, and that's what you get. But this is what you write out. So this is the Ka for this amphetamine. Okay, was that a good review? Okay, great. So let me erase this because we got other stuff popping up. Now this is, do you see what this name is? A lot of times you got to look at the chemical name. I don't know what amphet is, but I know what an amine is. Okay, and I see amine, I know there's an N somewhere, a nitrogen, a basic nitrogen. And so this is going to be a base. So I'm just going to take this complicated name. I don't, at this point, know what the molecular formula is. So I'm just going to call that B. That's base. I know it's a base. So I've got B plus water gives me the protonated base plus a hydroxide. You see the base is producing hydroxide when it dissolves in water. Okay, so that is our reaction that we're going to do the ice table with, the equilibrium. And so here's our Ka. This is a basic reaction, so we can't use Ka. Ka would be for the acid form. So this Ka is related to BH plus. It's just the chemical convention that we use Kas for everything, even for bases. So we really need Kb for this reaction. So how do we get to Kb? Well, we've got this Kw, which is 10 to the minus 14. This is laggy right now. Okay, is Ka times Kb. So we could solve for Kb if we knew Ka. We could also do the minus log of all of those. We could take the pKw, and if we take the minus log of this product, we could get the sum of those two logs. And so this is 14 here, and this is 9.8 that's given in the problem. And so we could figure out what KB is. It's 14 minus 9.8. So that would be easy to do. And so here's our KB reaction. So we see that it's KW over KA, which is then 6.3 times 10 to the minus 5. That's our KB. So that's the equilibrium constant for this reaction that's written here. So we have our governing equation for this equilibrium. It's the equilibrium constant. So let's look at the ice table. We start with the initial, we have a change row, and then we have equilibrium, ice. Initial, change, and equilibrium. And we're starting with 2 molar solution of base. So that's what we call the nominal concentration. Let's say we're making up this stock solution. We concentrated it up to 2 molar amphetamine, okay, in water. And it doesn't stay that way. As soon as we put it in water, Le Chatelier's taxi takes over and establishes equilibrium. Okay. So we have some of this going away. That's why we have a minus X. We don't include water because it's a pure liquid. Don't include pure water. So it doesn't have a column in the ice table. Then we have the double-headed arrow, and that's where the signs change on the X's. You see these are pluses over here because they're on the product side. So the reactants are going away, minus X. The products are showing up, that's plus X. And so then at equilibrium, we'll have 2 molar amphetamine minus a small amount. And it will be such a small amount, we won't notice that 2 molar is less than 2 molar. Like we're gonna assume this, and we will check this assumption later. So the number 2 minus a tiny little x, when you look at the significant figures, you can't tell that you've subtracted anything. So it's roughly equal to 2. But we have 0. If you have 0 and you get anything else, it's significant, right? So anything added to 0 is significant. So we don't assume that these are 0 anymore. We assume that they're x. If anything shows up on the product side, we'll be able to detect it as x. And so now we can write out that equilibrium constant expression. So this is the KB. And you see that this equation over here, we have the OH on top and the BH plus on top, and both of those are x, so that's where we get the x squared. Is this coming back to you? It's been a while. Okay, good. And then we can solve for that x, the square root of the nominal concentration, so CB times KB. Take the square root. And we end up with 1.123 times 10 to the minus 2. That's the hydroxide concentration. Now, what is the problem asking for? It's asking for the pH, which is the minus log of the hydronium ion concentration. So we need to figure out we could do the POH, which is 1.9. So the minus log of that number is 1.9. And then we know that this autoionization constant of water is the governing the balance between hydronium ion and hydroxide ion. So if hydroxide ion goes up, the hydronium ion goes down, and vice versa. They all add up to 14. So we end up with this being 14 here is equal to pH plus POH. So pH is the pKw, 14, minus the POH, 1.949. So 12.05 is the pH. That's what the problem was asking for. We did it. It seemed a lot harder in the freshman year, didn't it? What's the thing that bothers you about these types of problems? The what? A lot of steps, yes. The ice table. Which piece of the ice table bothers you? I know which piece bothered me when I was studying it, but I want to hear what you. The minus x plus x, yeah. Did it help? Right under the double arrow, that's where the signs change. Okay, so just products, reactants. Products are going away, reactants are showing up. The equilibrium constant expression? Yes. Okay, now this one was tricky because we got a pKa and it was a basic substance. Right? That's level 2. We jumped right into level 2. Okay. But we had to come up with that equilibrium constant expression for this reaction, not for the acid, right? I think the thing that confused me when I first started out was this piece right here. When can I make that assumption? Right? Because I have 2 minus x, and all of a sudden it's just 2. I don't use the minus x. So, am I comfortable with that? Yes, because look here, we solved for x, and it's a really small number. Okay, so let's write this in decimal form, 0.0123, right? 1 times 10 to the minus 2, okay? And so it really should be 1.99, right? But that's pretty close to 2. If we subtract 0.01 from 2, it's really close to 2. So you can always check your assumption. You can assume x is small, solve for it, and then look. And like, ooh, it really wasn't that small. You know, I needed to incorporate it into that number. I couldn't really ignore the minus x. You know, but in this case I could. I'm only, 0.5% off or something like that. Okay, so this assumption is valid or is okay if this C base, this is C base here, the nominal concentration of our base, divided by Kb is greater than 100. Then this will produce less than 1% error. Okay. And so we got 2 divided by 6.3 times 10 to the minus 5. So just think on the 10 to the minus 5. We got 2 times no tens, right? We got 2 divided by something that's 10 to the minus 5. So that's way bigger than 100. Okay. So we're okay with that assumption. Okay. Now, sometimes we want to calculate what's the percent ionization. And so percent ionization is the ionized species here, this BH plus, divided by all of the base species. So we have the ionized and the unionized. So it's part over whole. So the ionized part over the whole. We know the whole was 2 molar. So we put 2 molar in solution and it broke up into some ionized and some unionized. But that's the whole, 2 molar. What percent was the BH plus? So 0.01123 over 2 times 100%. So it's 0.56%. So not even 1%, certainly not 56%. Like don't multiply by 100 again. It's already multiplied by 100 and it's 0.56%. So that's an important thing to know. Not very ionized. Because we put this base in pure water and there's, it's not very protonated, so it's just barely soluble. Yeah. So okay, now let's do an ice table in the worst possible case where we have to use the quadratic equation. Okay. Yeah, so we have the same problem, but now instead of 2 molar, it's 0.0025. So we take that number, divide by Kb, it's not above 100. So we're going to have to keep that minus x. Okay, so we got the same equilibrium or ice table. You have the base, this is the double-headed arrow part right here. Okay, and the BH plus and the OH minus. We do the minus x's and the plus x's, and now we have 0.0025 minus x, and then x and x over on the product side. And so this is our equilibrium constant expression. And it gets way more complicated when you have this right here. That means I have to use the quadratic formula. Okay. And so in order to use the quadratic formula, you've got to get it in the standard form. You have to have 0 equals ax squared plus bx plus c. So you have to have it in that standard form to use the quadratic formula that we've all memorized. Okay, so I'm moving things around. I move the denominator over there, multiplied by kb. Then I have x squared here. So I'm going to multiply that 6.3 through. Okay, and so I have it now times minus x, and then I have it times the 0.0025, so that gives me this number here. And then I moved it, and so you guys can check your algebra, make sure that you understand all the steps that went through this. So I have this standard form of a x squared, so a is right here, it's 1. So a is equal to 1, plus bx, so this is b, plus c, so this is, c is negative. And then this is the quadratic formula, the solution to those roots of this quadratic equation. Minus b plus or minus the square root of b squared minus 4ac over 2a. And so let's just put all our numbers in there. It's really ugly, but so what? You know what to do. It's what I say, it's not difficult, it's tedious. So you just got to not make a mistake. So here's all of the pieces. Minus b and b squared and 4ac. A is 1, so that's why we don't see any a's in here. And then divided by 2a. So 2 times 1 is 2. And we get this value. Now notice I've used the plus here because this is plus or minus, right? And so I've got a plus root. And so this is a way to keep track of it. Write this root as x plus, indicating you use the plus on the quadratic formula. And then this one is x minus. So this one has the minus sign. So this is the minus root. It just so happens it's negative, but that's not always the case that it'll be negative. It just shows that you, in the plus or minus choice, this is the minus one. The x plus is using the plus sign. And so we get two concentrations, and that's always problematic because you're looking at it and you go, how do I know which one to use? Right? Because I've got two concentrations. I got two answers for my x. Yeah. Yeah, so this negative one doesn't make sense because it's a negative concentration. So that doesn't make any sense for the issue. So for a negative x, think about what would happen here. I would put in 0.0025 amphetamine, and it's minus a negative x, so then it grows. I like get amphetamine out of nowhere in solution. So I put in some and I get more. That doesn't make any sense. So we have to use the positive root. And so our x value is this 0.000367. So it's right there. So we could take the minus log of that and get the POH at 3.44. And then subtract that from 14 to get the pH. And here's the answer to our problem, 10.56. Now, it's always good in these problems to think, did this make sense? Last calculation gave us a pH of around 12, and the base concentration was 2 molar, and this base concentration is really, really small, and it has a less basic pH, so that makes sense. This only has a pH of 10, whereas the last one had a pH of 12. The stronger the base, the higher the pH. So. Just giving you time to write. Okay. And so then we could put in the actual amounts. And so if we put x in there, it's a small number. And look what it did. It went from 0.0025 here to 0.0021. So it changed in the second significant figure. So yeah, x was substantial. Even though it's tiny, we had a tiny starting concentration. So it took away a substantial amount of that base. And then we could do the part over whole. We could take this amount right here and divide it by the whole. So 0.000367 over 0.0025. times 100%. And that would give us our percent ionized. So we're 14.7% ionized. So we have a tiny amount of base and 14% of it ionized because it's such a small amount. And water, just the pH balance of water would be enough to ionize that much of this base, even though it's a weak base. Okay, so that's the quadratic equation. It's not too bad. It's ugly, but like I said, it's not hard if you know you get it in standard form, then use your definitions and A, B, and C, and just hammer your way through it. The most difficult thing for me is missing negatives. I'm doing my calculator and I'll screw up and miss a negative, and then I'll do it 3 times and I'll get 3 different answers. And I just get so frustrated. Yeah. Okay. Now, if we could avoid doing the quadratic equation, that'd be great. So here's a technique that allows us to avoid doing the quadratic equation. And this is also a technique where we can drive the equilibrium by putting in acid. So in this case, calculate the concentration of neutral amphetamine that remains in an acidic solution of pH 2. So totally different situation. So big emphasis on this. So we're driving it with acid. So this is using, like, we're picking the taxi cab driver here. We're going to use this acid. So no longer is it just interacting with water. It's interacting with an acidic species. So we have our amphetamine base plus H3O plus, which we can control because we have a pH of 2. So that's telling us with the concentration of this H3O plus. We have the double-headed arrow, we have the protonated base, and then we have pure water as a product. So this acidic hydronium ion is protonating the base, making protonated base and giving us pure water. So we just ignore the pure water. We have the double-headed arrow here. We have a tiny amount of base, which I look at that and I go, I don't like that because I don't want to have to use the quadratic formula. All right. And so what we're going to do is we're going to drive this completely forward. And this is a situation where if we wanted it to be totally protonated, we would put it in acidic solution because acids react with bases. So if we put it in an acidic solution, it's going to protonate that base and make it all go to the right. And so let's just pretend we went all the way to the right. Nature never does anything 100%, but we're in charge of the calculation. So we just drive it all the way to the right. So I've got my minus signs for my reactants and my plus sign for my product. And then we're going to push it all the way to the right by making the limiting reactant equal to 0. How do I know that the base is my limiting reactant? Because I'm choosing to put an excess amount of acid in there. So I'm putting it in an acidic solution of pH 2. And the base is such a small amount, it's not going to change the pH or the hydronium ion concentration very much. And so we're going to drive all of that base to the product side by setting this equal to 0. So when we set that equal to 0, we're able to calculate X. And once you calculate X, you get X for the whole table. There's only one X, right? We calculate that X, and we know it's 0.0025 because 0.0025 minus something equals 0. You took all of it away. And so now we bring it over here, and there's 0.0025 over here, the BH plus, we've got the 0 plus X is 0.0025. And then this it's not really changed much. We have 0.0100 minus this 0.0025. So it does change. So it goes from it's like 100 to 75, right? We subtracted 25 from 100. You can see that. And so we're going to take that into consideration. But now we know how much acid we have, how much protonated base we have, and we've taken this all the way to 0. But you know, nature hates zeros. It doesn't want to do everything 100%. We can drive it all the way to the right on paper and then let it come back a little bit. So now we've got a new initial. So you see we've got a new initial row. We've got, this is now the reactant. It's the protonated base, and it's going to react with water and produce some hydronium ion concentration and some residual deprotonated base. So look at my signs. So the reaction's going this direction now. So this is a minus sign because this is the new reactant, and this is a plus sign because it's a product, and this is a plus sign because it's a product. And so if we run that reaction backwards, it's not going to go very far backwards. So we have that 0.0025 minus a tiny little x, which is going to be insignificant, and we'll test that. And it's going to produce this 0.0075 plus such a tiny x we won't detect it, so we don't have to take into account the x here. But 0 plus x, anything plus 0 is significant, and so we're going to keep that x. So here's our equation. It's that Ka, so we're doing that. This is the acid reaction, so this is our A. So Ka is 10 to the minus 9.8, and it's the products over reactants. So it's X times the 0.0075. This is B, this is H3O plus, and this one down here is the BH plus. We put all those numbers in, and we can see that X is a tiny, tiny little number. 5.3 times 10 to the minus 11. That is so small. That's less than 1 in a billion. Okay? It's like 10 in a trillion. So there's very little B there. Why? Because we drove it to the right by adding acid. We added acid, and all of the amphetamine went to BH plus. The only amount of amphetamine left over is 10 to the minus 11. It's insignificant, almost, well, it's not detectable. Okay, so this is a way we use Le Chatelier's principle to force all of that B to be BH plus. And if we can detect BH plus, we've been now able to detect the full concentration of our base, not just 5% of it or 56% of it or 0.56%. We're getting all of it. So it's 100% ionized, and we can detect it easily. Okay. So this shows that if we have a low pH, which this is a low pH, a pH of 2, right? Neutral pH is 7, so we're at a low pH. We're in an acidic environment. Look at the stomach. pH of 1 to 3, depending on what I ate for lunch, right? And so bases are protonated. And notice we did this for amphetamine, but this is a generic B, a base, okay? So if it has a pKa above 7, this is going to happen. So all of the bases are going to be protonated if you put them in acidic solution. So because bases are protonated in the stomach acid protonates those bases, and your bloodstream is an aqueous system. And so they're in solution now, and they can pass through the membranes in the stomach and go right into the aqueous solution in the blood. So this is how we absorb basic molecules. We absorb them in the stomach. So if you're going to make like a headache relief powder or something like that, you want it to be basic. You want it to be an organic base because that's absorbed fastest. As soon as it hits the stomach, it's protonated, goes into the bloodstream. If you want something that's going to be a time release, you want to either protect it so it doesn't dissolve. You protect it with an acidic coating so it's protected through the stomach, and then it falls apart in the intestines. The intestines are 5 to 7% in the small intestines, or 5 to 7 pH in the small intestines, and a 7 to 8 in the colon. So acidic substances will be deprotonated in the colon and are more soluble. So the pH of your digestive tract is sort of absorbing different things at different places. So let's look at some of the drug absorption. These buffered places in the stomach make the problem super easy because we know how much acid we have in each of those. So in this case, we've got the pH of the stomach. We can look at, you know, how much base. Here's our phendimetrazine tartrate. So here's a base. You see it's a protonated guy right here. pKa is 7.6. That's greater than 7, so it's a basic substance, very weak base. And if we just look at a buffered pH, a pH of 1, like in the stomach, a pH of 1 here, this is telling us that our concentration is 0.1 molar acid. And so we're not, you know, BH plus, none of it goes away because it stays protonated. We have sort of the common ion effect. We've already got so much acid that this is not going to make more. Okay, and so very little of it will form this deprotonated base. So it just remains 100% ionized. We can solve that using this equation here. So we have the H3O concentration of 0.1, BH plus of 1, and then we can solve for X, which is the B concentration, and we can see that it's a tiny amount. It's 2.5 times 10 to the minus 7. So our bases are protonated in the stomach. Let's look at the colon. Let's just take an average pH of about 7.6. So now we convert that. 10 to the minus pH is equal to 2.5 times 10 to the minus 8. We can do our X's. If any of that goes away, it shows up as deprotonated base. But notice that when we're in the stomach or in the colon, it's buffered. So the pH remains unchanged. And so we have 1 minus X, X, and 2.5. Let's just keep that 1 minus X and do the math that way. So we have 10 to the minus 7.6, which is actually, coincidentally, 2.5 times 10 to the minus 8. So these numbers are equal to each other. And so we end up, this essentially, these two cancel. We have 1 on the left. So we move that over. We end up with 1 minus 2x. And so x is equal to 0.5. So in this case, our basic substance is 50% ionized in the colon. And that's not as good as it being ionized in the stomach. Like it was 100% ionized in the stomach, but this base will, if it makes it past the stomach, it's 50% ionized in the colon. So you would think of the percent ionized, think of that as percent soluble. So it's like 50% soluble in the colon, 100% soluble in the stomach. Does that make sense? Yeah. So let's say 50% of it dissolves in the colon or is soluble in the colon. Where does it go? It goes in the bloodstream, and now it's missing. And so then 50% of the next breaks apart. So it's kind of like half-life, right? We take away half, that goes into the bloodstream. And the colon tries to come back to equilibrium by producing half of what's left. So then now we have a fourth and a fourth, and then that goes into the bloodstream. And so it reestablishes the equilibrium, and we have an eighth and an eighth, and then that goes into the bloodstream. But you see how now you've got a time release, you've got an exponential decay of a half-life. And so all of these absorption and distribution things follow first order kinetics of half-lives. And so we'll be able to do that in another few weeks. We'll get into the pharmacology and how things will be distributed in the body. And absorption follows first order kinetics, and so does elimination. Because this substance is now in your bloodstream. What does your bloodstream do? It goes to the kidneys. And a certain percentage of that is eliminated into the bladder. Okay? And it goes around again. And then that's eliminated and is missing, so it's not in the bladder. So then the kidneys will establish another equilibrium and take a little bit of it away. And so you'll have a biological half-life of your elimination too. So you absorb it on a first order kinetics absorption curve, and you eliminate it on a first order kinetics elimination curve, and you can calculate what your peak concentration would be. And we're going to do a little bit of that in the future. Now this idea of percent ionization, this is how we've been calculating it here. So let's just do it, for example, for an acid. Okay, so this example is for an acid. Remember I said it's part over whole. So the whole is both the ionized and the unionized part, and the part is the ionized. So we're looking at percent ionization. So it's only the one that has a charge. Okay. Now let's flip this whole thing upside down. And then we can split this denominator among the two pieces in the numerator. So we can put HA over A minus and A minus over A minus. So is everybody okay with this step? So when we split the denominator, now we have 1 over here, HA over A minus. Okay. And now let's move this 1 over to the other side and reverse everything. So we have HA over A minus is equal to 1 over percent ionization minus 1. Okay, so let's put that in our pocket, and we'll use it later. Okay, just set that aside. Now we have the acid equilibrium constant here, products over reactants. So we have a HA plus water is in equilibrium with H3O plus A minus. All right, so that acid reaction gives us this equilibrium constant expression. You should be good with that. And we notice that here's the H3O plus. If we take the minus log of that, we get the pH. And if we take the minus log of the Ka, we get the pKa. So yeah, minus log of Ka is that right there. And so if we did the minus log of the hydronium ion concentration, we get the pH. And then we have the minus log of A minus over HA. If you don't like this minus sign, like Henderson and Hasselbalch didn't like that minus sign, so they just swapped these two things. They swapped the pH and the pKa. So they moved the log over to the other side, and they solved for the pH. So the pH is equal to the pKa plus the log of the anion over the parent acid. And they got their name on an equation by just doing 2 steps of algebra, and that's not right. This is the equilibrium constant expression. They did 1 step, 2 steps of algebra, and they get their name on something. Huh, yeah. So what if we take this A minus over HA, we pull that piece out of our pocket over here, and we stick that in there. And then this is buried way in there. Let's solve for percent ionization. So let's move this log over so it's got a positive sign. So we move this over to the other side of the equal sign, and we move the pH over to the right. And so we have this piece right here. And let's get rid of that log by raising both sides, 10 to the both sides. And now let's solve for this little guy in the bottom. So we've got to move a 1 over to this side here, and then we got to flip everything upside down. So this is my equation for buffered percent ionization, and I call it the Williams equation. No one else calls it that, but I do, so I can pat myself on the back. A whole lot more algebra than Henderson and Hasselbalch did, so I think it's justified. But the thing is, when you have a shortcut equation like this, you've got to know when to use it. And so let's look to make sure we don't screw this up. This is the percent ionization for an acid, not a base. Okay, like I'm pausing for effect. Okay, so this only works for HA, for acids, like naproxen, sodium, the acid form of that molecule. So if we have a neutral acid, okay, and it reacts with water, it'll produce this anion, and that's what we're talking about. That's the ion. This is the ionization piece, and this is telling us the percent of this guy right there. It's a product, okay? All we need to know is the pKa and the pH of the solution. So if I know the pH of the stomach, I can calculate the percent ionization if I know the pKa. If I know the pH of the colon or the small intestine, and I know the pKa of the substance I have, then I can calculate the percent of that acid that's ionized. Okay, but for bases, the reactant is ionized, and so it's that same equation, but it's inverted. And so let's just take 1 minus that, or 100 minus that. If we calculate percentage, then it would be 100 minus the percent ionized acid. So we can just keep that same equation, the percent ionized for an acid, and if we have a base, we just take 100 minus that. It's because the base, it's the reactant that's ionized. For the acid, it's the product that's ionized. So it's the same sort of, this is kind of like percent product. And so since it's the reactant that's ionized, we take 100% minus that number. And that'll tell us how much of a base is ionized. So let's check our work. We had our base was 9.8. So this was our pKa for our base. And we checked it in the stomach, which was 1 to 3 pH, right? And so in this region here, we're way up here. Our base was 100% ionized in the stomach. Do you remember the problem? The 9.8 was the pKa for that base. Okay. But then when we got to a pH of 7.6, we were over here, and it was the bases. It came in to be, we had a base that was 7.6 was the pKa, and we were at a pH of 7.6, and it was right here at 50% ionized. So that's where this guy crosses. And it's a drop down to where those things cross. And so you can know that too. If the pH is equal to the pKa exactly, you're right at the midpoint. You're at 50% ionized. So how do we know? Well, think about the pH. pH is the amount of protonation you can do. So if you're at a low pH, you can protonate all kinds of things. And so if you protonate an acid, it becomes neutral. If you protonate a base, it becomes charged. So bases are soluble in low pH because they're protonated. And acids are not soluble in low pH because they're protonated and they're neutral. If you're at a high pH, you're pulling protons off of things. You're in a basic solution, and so it'll rip protons off of stuff. If you rip a proton off an acid, it's now an anion, and it's soluble. We rip that proton off of a base, now it's just a base molecule. It's an organic substance. It's not soluble. It's not ionized. So understanding the chemistry is really the way to go. You need to think in terms of atoms, ions, and molecules. What is an acid? What does that word mean? Okay. Just think of HA. If I deprotonate it, I've taken H away and I've got A minus. That's soluble in water. I've got a base. What does it mean? If I protonate the base, I put an H plus on it. H plus. Now it's positive. Now it's going to be soluble in water. So you protonate a base, it's soluble. You deprotonate an acid, it's soluble. So you got to know the molecules, or at least the kinds of molecules. So we'll do some of these problems next time, this liquid-liquid extraction, but again, we've got quinine. It's a dibasic molecule with pKa's of 5.1 and 9.7. And so this is the skill that we'll be using next is say we have quinine, we'll just call it Q, okay? And you can think of pH here. You can write out a scheme. So this is a pH of 1 and a pH of 14. And so here we have pKa's of 5.1. So right around here we'll do 5.1. And over here is 9.7. So what kind of species do we have in these different regions? So if this is quinine and it's a dibasic molecule, we're going to put it over here where it's just quinine. If we go past 9.7, what does it become? That first base becomes protonated. So we have QH+. Does that make sense? If we get below 9.7, we've protonated it. And then if we go past 5.1, we have QH2, 2+. We have two bases in this molecule. We've protonated both of them. And so now we have QH2, 2+. So it's doubly protonated and is super soluble. Okay. So this is the skill that we'll take into the next thing when it's also in the homework. So when you start doing the homework, think in terms of the species. Basic molecules are going to be neutral at really high pH. What if we had an acid? What if we had a, let's do phosphoric acid, H3PO4. It was a pKa of, let's say, 3, 8, and 13. So this is an acid, right? H3PO4. This is the neutral species, H3PO4. When your pH is below 3, what happens when you go past 3? H2PO4 minus. We've deprotonated it. Now it's negative. Okay, it's an anion. We go past H, HPO4 2 minus. And then we go past 13, it's PO4 3 minus. So this is called a speciation chart. So draw your pKa's and then think about where things are ionized and what their formulas are. And this will help you in the liquid-liquid extraction piece, because we're going to put this in contact with an organic phase. And these two are going to be aqueous. And this is going to be organic because it's not charged. So that quinine or organic molecule is going to go right into the organic phase because it's not charged. Okay. Okay. And so here's just talking about the solubility. You have generic groups like acids, again, soluble in basic substances. Basic amines are soluble in acidic substances. What about things like amino acids? They have a base and an acid on both ends of the molecule. And so at neutral pH, the acid proton's gone from the acid and is over on the base and it's doubly charged. So it's got a minus at one end and a positive at the other end, and it's really soluble. And so you protonate it even more, and it'll become more soluble on the acid side or more soluble on the base side. Okay. All right. So that's enough for now.